Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of week 3. We are talking about induced strain actuation and its analysis for a one dimensional beam, and the analysis was static analysis, and we started with the Euler-Bernoulli beam method. We looked into few cases, and here we will see one more case. Now the beam is again fitted with, it has two actuators at the top and bottom, and they are similar actuators, but the voltage applied is different. So the voltage at the top and voltage at the bottom is different. So they can be same direction wise, they can be opposite in direction, but their magnitude are different, and that creates a lot of difference. So it would induce both extension and bending. So what we can do is, we denote the voltage at the bottom as V bottom and the voltage at the top as V top. Now what we do is, we decouple these voltages into a pure bending and pure axial case. So we assume that there is a voltage V1 and same voltage V1, and there is voltage V2 and a voltage minus V2. So V1 and V1 they induce pure extension or pure contraction, and V2 and minus V2 they induce pure bending, and their combination gives us the actual voltage V top and V bottom. So when we superimpose these two, we get the V top and V bottom and V top. So V1 plus V2 is equal to V bottom as per our consideration, and V1 minus V2 is equal to V top, which is shown here. Now if we solve these two equations, we get V1 and V2 in terms of V top and V bottom. So V top and V bottom are given to us, V1, V2 we do not know. So by solving this, we get V1 and V2 in terms of V top and V bottom. So this is what is going to cause a pure axial effect, and this is what is going to cause a pure bending effect. So as we have decoupled the problem, now we can solve this problem separately, as we have solved the pure axial problem, and we can solve this problem separately as we have solved for the pure bending problem. So for the axial problem, we can find out NP. NP becomes 2 multiplied by EC, BC, TC into epsilon P1. Epsilon P1 is the free stress corresponding to voltage V1, free strain corresponding to voltage V1, and this epsilon P1 is in terms of V1 D31 multiplied by V1 by TC. TC is the actuator thickness, and this can be written as EA total into epsilon 0, which we have been doing so far. So by solving this equation, EA total epsilon 0 is equal to this NP, where NP is this, we can find out epsilon 0. Now we find out MP. MP is EC, BC, TC, TC plus TB epsilon P2. So epsilon P2 is free strain corresponding voltage V2. So, we have epsilon p here, we have the opposite epsilon p here, and that creates a moment, and if we find out that moment we get this. So, the corresponding to this epsilon p2 we find out the moment here. So, we have to have this elastic modulus, and that should be equal to E I total multiplied by kappa, and if you solve this equation, E I total multiplied E I total kappa is equal to MP, we can find out kappa. So, if we separately find out epsilon 0 and kappa, and then we can superimpose the results, and that would give us the actual solution. Now, we will look into another problem where we have asymmetric actuation. It is asymmetric because although we have two piezoelectric patches, but their thickness are different. So, this thickness we may call as TC bottom, and this thickness can be called as TC top. Now, even if it is actuated with same voltage at top and bottom piezo, free strains can be different. Because if you look at the expression of the free strain, there is Tc sitting at the denominator. So, that would make the free strains different. So, to solve this problem, again if we look at the cross section, the cross section can look like this. To solve this problem, we take z is equal to 0 at the mid of the beam. So, EA total becomes EC AC top. EC is elastic modulus of the top piezo, AC top is the area of the top piezo. So, AC top is BC into TC top. So, AC top is BC into TC top, and AC into AC bottom, where AC bottom is BC into TC bottom, their width are same. So, both are BC, and then we have AB, area of this beam section, which is BB into TB, and now we find out ES total. Now, as this section is not symmetric with respect to this line, this z equal to 0 line, ES total is not going to be 0, this is going to be non-zero. So, we have some ES total which is non-zero, and that is this, and then we find out the EI total again with respect to this line. So, in the EI total, this is the contribution from the bottom piezo, from the top piezo, and from the beam. So, we found out our EA total, ES total and EI total, and because the section is not symmetric, ES total remains here. Now, we find out our NP and MP. In the similar process that we have adopted so far, we can find out our NP. So, NP is, so this is the NP, and although the top and bottom voltage are same, so just to show it, it has been written separately, V top and V bottom, and MP is this. So, we find out the moment with respect to the z equal to 0 line, and that becomes our MP. Now, when Vc top, when V bottom and V top is equal to V, we get this as our NP and this as our MP. And finally, this is the equation that we have to solve. Here, because ES total are non-zero, so these two equations are coupled, and by solving this coupled equation, we can find our epsilon 0 and kappa. Now, in this case again we have dissimilarity, but here the dissimilarity in terms of the D31. So, the D31 at the bottom piezo and top piezo are not same. So, again we can say that under same voltage free strain can be different at the top and bottom piezo can be different, So, epsilon P top is the free strain at the top piezoelectric patch, which is this. Epsilon P bottom is the free strain at the bottom piezoelectric patch, which is this. NP, the axial force corresponding to the free strain, we can get in the similar fashion, and MP, the bending at the bending moment corresponding to the free strain, again we can get in the similar fashion. So, this is what we get as NP and MP, and then after that finally the equation looks like this. Now, here one thing to note is that we would find out ES total, EA total and EI total in the same way. Now, the two piezos are different. So, if the or if EC top is equal to EC bottom, in that case ES total is going to be 0, because the section becomes symmetric with respect in terms of the elastic properties. But when EC top is not equal to EC bottom, ES total is a non-zero value. So, in that case we have to solve the coupled equation. If ES total is 0, then we can get rid of these two terms and the two equations get decoupled like this, and if they are not same, then we have to solve the coupled equation. So, this leads to this situation and this leads to this situation. So, with that our static analysis under induced strain for one dimensional cases using the Euler-Bernoulli beam technique is finished. Now, we will go to a next technique called the block force space method. Block force space method is a very approximate method, it is highly approximate, and it has some more assumptions. So, first of all it is highly approximate. It considers the effect of the actuators as line forces and variation of stress, strain along the length or thickness of the piezoelectric actuator is neglected. So, the stress strain along the length and thickness is assumed to be same, and effect of this actuator is considered as a line force. We will see that in the next slide. Again we will look into those same cases that we did for the Euler-Bernoulli beam based technique. So, the first is the extension case. Extension case, as we know, they are actuated with same voltage. Now, if the actuation is such that this piezo contracts the both the piezo, so that is why the piezoelectric patch is under compressive force, tensile force, and the beam is under compressive force, and it happens in for both the top and bottom piezo, and all these forces have same magnitude F. In these problems, the unknowns are our F's, which if we can find those, we can solve the problem. The case can be reversed. The actuation can be such that the piezoelectric patch tries to expand. If the piezoelectric patch tries to expand, the effect just becomes reverse. The piezoelectric patch experiences a contraction force, a compressive force, and the beam experiences tensile force. Similarly, here and here, and again the magnitudes are we denote as F. So, as I said, in this approach, our unknown is F, and we try to find F by imposing the condition that the displacement at these junctions between the piezoelectric patch and the beam is same. The compatibility of displacement we impose, and by imposing that condition we try to find out our unknown actuation force F. So, if we try to do it for the pure extension case, we have to find out the axial deflection of the beam, I mean the expansion of the beam, I would say, at or the contraction at the junction between the piezoelectric patch. Now, it is because it is axial effect. So, the effect is same whether at the top junction or the bottom junction or in between those, it does not matter, everywhere it experiences same expansion or contraction, and that is denoted as delta LB. Now, delta LB is, if we see, we have a force F and we have a force F. So, the total force experienced by the beam at here is 2F. So, if we divide this 2F by this area of the beam, which is AB, that gives us the stress, and then if I divide by the elastic modulus of the beam, that gives me the strain, and because the strain is same in this zone, in this actuated zone. So, we can just multiply this by LC, the length of that actuated zone, and that gives me my expansion or contraction of the beam, that is delta LB. Now, I can replace AB by BB TB, and this is my full expression for the expansion or contraction of the beam, the axial deflection of the beam. Now, we need to find out the length of change of piezo actuators. So, for the piezoelectric actuators, the length of change in length is this epsilon p minus F by BC TC EC multiplied by LC, which we can verify here. We know that the stress in the piezoelectric patch is EC multiplied by epsilon minus epsilon p. Now, epsilon is the stress. To get the stress, we have to get it from the force, from this force F. Now, we are denoting the force in the beam as F. So, in the actuator it is minus F. So, it is minus F divided by BC TC is equal to EC E minus epsilon minus epsilon p, and then by solving this we get the expression as epsilon is equal to epsilon p minus F by BC TC EC. Now, if this is my epsilon p, from here I can find out the changing length. We just have to multiply with LC. So, we get delta LC is equal to LC multiplied by epsilon, and that is equal to LC the entire x thing multiplied by epsilon minus F by BC TC EC. So, this is what we can see here, and then epsilon p can be written as V by TC, and this is our final expression for change in length of the piezoelectric actuators. Now that we have found out the change in length of the beam and changing length of the actuators, we have to apply the condition of compatibility. So, we apply the condition here. This is our compatibility condition, compatibility of displacement, and that says that delta B is equal to delta LC, delta LB is equal to delta LC, delta LB is taken from here, delta LC is taken from here, and they are equated. And after equating those, we get F as this. Now, this expression can be written in a more compact way. So, we take DC VC by TC by 2 here, and here I have EAB, EAC, EAB plus EAC, where EAB is the area of the cross section of the beam, and EAC is the combined area of cross section of the two actuators. So, 2 EC BC TC, I mean it is EAC. So, apart from area we have to factor it by elastic modulus also. So, they are here. Now, DC VC by TC is my epsilon p. So, epsilon p divided by 2, and this remains same, and then we have to, then we can write this entire thing as in terms of the block force also. We know that block force is FBL is equal to epsilon p multiplied by TC BC into EC, and TC BC EC is the TC BC is the area of one actuator. So, TC BC EC can be written as EAC divided by 2. So, epsilon p is equal to twice FBL by EAC. If we put it here, then the expression in terms of block force becomes this. So, this is our actuation force in terms of the free strain or in terms of the block force. Once we get our actuator force, we know everything. Now, we can find out how the beam responds to the actuation. So, if we just go back to the previous slide, after we know the actuation force, so the actuation force acts here, then so this beam is under force 2F twice F. So, twice F divided by the area is our stress, and that divided by its elastic modulus is the strain. So, it is EB beam elastic modulus, and then again it can be further simplified written in terms of either epsilon p or FBL. Now that we know the expressions for the force and the strain, we can see some extreme cases now. If our EAC is much more than EAB, then this expression for block force, if EAC is much more than EAB, then this expression becomes 0. This tends to 0. So, block force becomes 0, and when block force is 0, which means the actuator is expanding freely, and that is also evident from the expression for EB epsilon B. In the epsilon B, if I say that, if I put the condition that EAC is much greater than EAB, then this tends to be 1. In that case, epsilon B becomes epsilon P. So, here because piezo stiffness is much higher than the beam stiffness, so the piezo experiences less resistance by the beam or the bar. So, it can expand in its own way. So, it does not feel any obstruction, that is why the block force is 0 and it expands freely. So, the strain is equal to the free strain. In the reverse case, when the piezo stiffness is much less than the beam stiffness, in that case it experiences quite a bit of obstruction by the beam. So, the force is equal to the block force. So, again if we put the condition that EAB is much higher than EAC, this becomes 1, then F becomes FBL. So, that is what we see here. On the other hand, when the force is just equal to the block force, which means the piezo is not able to deform or expand, in that case epsilon B is equal to epsilon B is equal to 0. So, that is what we see here. When yes, so in that case when our it's 0. So, this is what we see here. So, these two are the reverse cases, the effects are opposite. Now, with that I would like to conclude this lecture here. In the lecture we will see some development of this case itself, and then we will move on to a few next cases. Thank you.